welcome all to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College. The subject that I am covering in my lecture series is Microprocessor. KCS 403 is the code. Today I will discuss about Microprocessor 8086 instruction formats and assembler directives. So 8086 instruction format vary from 1 to 6 bytes in length. As shown here, these are the instruction formats. I will discuss these one by one. Displacements and operands may be either 8 bits or 16 bits long depending upon the instruction. Opcode and addressing mode is specified using first 2 bytes of an instruction. How? We will see. So these are instruction formats. Here 1 byte instruction is having this format. Simply 1 byte is presenting the opcode. Here maybe 1 byte instruction with register mode is there, so it will be presented by this opcode and register. In register to register addressing, it is given by opcode, and 1 here represents the register addressing mode. Here this is the register name and this is the register or memory. So this is the instruction format. Here again register to or from memory with no displacement. It is also having the 2 bytes of instruction format. First byte represents opcode, second byte gives mode, register, R/M, that is, it may be register or it may be the memory. Then register to or from memory with displacement of 8 bits. So there was no displacement. Here it is the displacement of 8 bits. So 1 more byte will be consumed for displacement. First byte represents opcode, second byte represents mode, register and register or memory pointer, and third byte represents displacement. If there is 16 bit of displacement, then this displacement is replaced by 2 bytes of displacement. First byte is for the lower order displacement and the last byte is for the higher order displacement. Now immediate operand to register, that is, now here the operand will be there, will be present. So the third byte will be occupied for operand. So first byte represents opcode, second, since this is the register addressing mode, so 1 represents register addressing mode. Next opcode is there, then register / memory pointer, and third byte is for operand. Now immediate operand to register and 16 bit operand is there. So 1 more byte will be added for the 16 bit representation of operand. So this first byte represents opcode, second byte represents the mode, opcode and register / memory pointer, and third byte for lower order operand and last byte for high order operand. Immediate operand to memory with 16 bit displacement. So again, since it is the first byte is representing the opcode, second mode, opcode, register / memory. Now this is for the operand and this is for the displacement. So this part is for the operand, lower order, and this part is for displacement, lower order displacement, higher order displacement, and this part is for operand, that is the lower order operand and higher order operand. So in this way all instruction formats are defined here. So we come to the conclusion that the opcode or the addressing mode byte may be followed by, so this byte, so this is the opcode or the addressing mode byte. This may be followed by the following options. Maybe there is no additional byte, maybe there are 2 bytes of effective address for direct addressing, maybe there are 1 or 2 bytes of displacement, as I have already discussed here. So the third byte is always a displacement or the operands or whatever the case may be. So these are the possibilities. So the third possibility is that 1 or 2 bytes of displacement can be there, 1 or 2 bytes of immediate operand can be there, 1 or 2 bytes of displacement followed by 1 or 2 bytes of immediate operand. This is also the case, this is the last case. Now 2 bytes of displacement and a 2 byte segment address, this may also be possible for direct inter-segment addressing only. So these are the possibilities of instruction formats for the third byte of instruction format. So now when we talk about the instruction format, this term is very important, that is 1 bit indicators. What are these indicators? Like there is W bit, this bit specifies whether we are working on the word or the byte. So when we are working with the word, this W bit is 1, if we are working with the byte, this W bit is 0. Now D bit, that will tell us that the register mentioned in the register part, okay. So the register is specified within the instruction, that is this part. This is the source register or the destination register. So if this is the source register, then this bit is 0. If this is destination register, this bit is 1. Now we come to S bit. An 8-bit 2's complement number can be extended to a 16-bit 2's complement number by sign extension. So in the signed numbers, the most significant bit is extended to the higher order byte, and this is known as the sign extension. So S bit along with the W bit indicates certain operations. Let us see what are these. So when both are 0 0, it represents 8-bit operation. When sign bit is 0 and W bit is 1, it indicates the 16-bit operation with 16-bit immediate operand. There is no sign extension present. Then there is when there is 1 and 0 for S and W, there is no operation, that is it is undefined. When there is 1 1 in each of S and W bit, then 16-bit operation with a sign extended 8-bit immediate operand. This is the condition. Another important bit indicators are V bit. It decides the number of shifts for rotate and shift instructions. So whenever we talk about the shift and the rotate instructions, certain counter should be there which represents that how many times the data has to be rotated or shifted. If this count is equal to 0, then if this if this count is equal to 1, just once we have to shift or rotate, then this V bit is 0. And if this count is greater than 1, then V bit should be 1 and the count value should be loaded in the CL register. Next bit is Z bit. It is used for string primitives such as repeat, REP, for comparison with the 0 flag. If this bit is 1, then instruction with the repeat prefix is executed until the 0 flag matches this bit. So in this way, this Z bit is used for string operations. Now the second byte which is defined in the format is given, maybe it is having this form or this form. So this portion defines the mode, then this opcode and this register oblique memory pointer. Then again another form is this portion represents mode, this represents the register, and another one represents the read, that is the register or the memory pointer. So what are the definitions for this part? Let us see. When this is 0 0, it means there is 0 displacement, that is lower order and higher order displacement are absent. If this is 0 1, only lower order displacement is present with sign extended to 16 bits. If this is 1 0, both low order and higher order displacements are present. If 1 1, then register oblique M field, this is treated as a register field only. So maybe there are 2 registers, so this field is also used for the register field, that is the register, for mentioning the register. So these are further definitions. When we are performing the word operation, that is W bit is 1, then the combinations of these represents the corresponding registers, and when the byte operation, when we are performing the byte operation, that is the W is equal to 0, then the values for the values for the register field, that is this field, it's equal to these corresponding to the combinations of bits. And when we are talking about the segment registers, then 0 0 represents extra segment, 0 1 represents code segment, 1 0 represents stack segment, and 1 1 represents data segment. So, all these definitions are for the register field, that is this field. Now, when we talk about the R/M field, this field, so this is the definition. So, for when 000 is present in the R/M, then it means that effective address is given by base register plus source index register and displacement. Similarly, for 001, effective address is given by base register, destination index register and displacement, and so on. So, these are the various combinations for this field, that R/M field, for this combination of bits. So, this is one and the same thing like this. This is just the explanation of that particular one. So, now let us have the look at the example. Move SP comma BX, that is move the value of base register into stack pointer. Now, what will happen? So, this is the instruction, this is the opcode, okay. So, 100010, this is the opcode. Now, another next bit is the D bit, that is the register which is mentioning in the register field here. The register which is mentioned in the register field is destination or source. So, if we go back to the table, so if we go back to this table 100, so 100 is represented by stack pointer and 011 represents BX. So, the register mentioned in this is stack pointer, that is the destination register. So, when we are having this part is storing the destination register, then this bit should be 1. So, this bit is 1. Now, since we are working on the word, since these are both 16-bit registers, so we are working with the word, not with the byte. So, this is again 1. Since we are talking about the register to register mode, so this is 1. Then, as I have already discussed, that this part is containing the destination code for destination register. So, it is 1. So, the destination register here is a stack pointer, and if we refer to the table again, stack pointer is having 100. So, here this is 100, register oblique M, this is another register and this is the source register. So, here the source register will come and the value corresponding to the bit combinations corresponding to BX is 011. So, here 011 is there. Since there is no displacement, so we are leaving these two fields. So, this makes 100010 here. Now, again 1 for again this 100 here and 011. So, this makes the whole 2 bytes of data, that is this one. So, in this way we can conclude the instruction format for this instruction. Now, again similarly we can have a look at this example. Now, both the registers have been exchanged. Now, this is the source register, this is the destination register. Now, here we are not changing this 100. Now, this is the source register. So, here the D bit will be changed. This is representing the register represented by this field is now source register. So, here this value will be 0. Now, again word, since we are working with the word, so this is 1. In this way this format is specified. So, this is again mode is 11 for register to register mode, and this is the destination register 011. So, in this way we can find out the instruction format for any of the instruction given in the question. So, for the instruction formats we had to just remember the tables, we have to remember the codes corresponding to the different registers, and so we can find out the instruction format for any of the given instruction. Now we come to assembler directives. Assembler directives is again a program used to convert an assembly language program into machine equivalent code. So this is the role of assembler. And then what is the assembler directives? The instructions given to the assembler during the execution of the program. This is known as the assembler directive. So these are also known as the pseudo operations. So first of all, the very first assembler directive for 8086 is assume, and it is used to tell the name of the logical segment the assembler to use for a specified segment. Example, assume CS colon code. It tells that the instructions for a program are in the segment named code. Another assembler directive is define byte. It allocates the memory for the bytes like ranks db, that is defined byte 01h, 02h, 03h, 04h. So this statement will direct the assembler to reserve 4 memory locations for the list named ranks and initialize with the above specified 4 values. Another example, value db 50h. This statement directs the assembler to reserve 50h memory bytes and leave them uninitialized for the variable named value. The next assembler directive is define word. So it allocates the memory, number of memory words instead of bytes. So it is similar to db, but here the words are allocated, that is the 16 bits are allocated. Like for example, here words, define word. So these are the 16-bit words, and this memory has been allocated for these 16-bit words, and it has been given the name words. Define quad word. It's used to direct the assembler to reserve 4 words of memory for the specified variable and may initialize if this specified value. So it is used to reserve 4 words, that is the 8 bytes. That's why the name quad. Now define 10 bytes. It allocates the blocks of 10 bytes to the it allocates memory to store the 10 blocks of 10 bytes and initialize the 10 bytes with the specified values. Now again and it represents the end of program. It marks the end of an assembly language program. End procedure, used along with the name of the procedure to indicate the end of procedure. Procedure root, start of procedure is there, and then if you want to end the procedure, then we have to write root and p. This is the name of the procedure, this is the assembler directive. Ends of segment. So if you want to end the segment, so this is given written with the help of end as. So it marks the end of the logical segment, and so here we will start the segment named data. Data ends, then assume CS code. So here it is assigning the name to the segment, and then code segment, code ends, so end as, that is the end segment. EQU equate, it means it gives a name to some value or symbol. Each time the assembler finds the given name in the program, it will replace the name with the value. So in this way equate can be used to give certain give the constants, give names to certain constants. So in this way it can be used. So like correction EQU 03. So 03h is the value which has been assigned to the variable named correction, and wherever I'll use this variable name, it means 03h. Even it tells the assembler to increment the location counter to the next even address. So it will align the address with the even addresses. So the writing procedure is like this: even, procedure root, and root and p. So it will align the addresses with the even, it will increment the address to the next even address. External and public. So this external means external and public means public. The directive external informs the assembler that the names, procedures or the labels declared after this directive have been already defined in some other assembly language modules. So these are external to the main module. So they are also available with other modules. And the public, while in the other module, where the names, procedures and labels actually appears, they must be declared public. So, in this way extern and public both are complementary to each other. Global, it can be used in place of a public directive or in place of extern directive. It is used to make a symbol defined in one module available to other modules. So, it can be interchangeably used with the public and extern directives. For example, if I define this divisor with the directive global, so now the divisor becomes public so that it can be accessed from other modules. Group, it is used to tell the assembler to group the logical segments named after the directive into one logical group segment. So, like this, using the group assembler directive, I can combine these segments within the segment named small. Include, it is used to tell the assembler to insert a block of source code from the name of file, from the named file into the current source module. This will shorten the source code. So, in this way we can include the external files. Label, it is used to give the name to the current value in the location counter. This directive is followed by the term that specifies the type you want to associated with that name. Length, it tells the byte length of the label. Its name, it is used to give the specific name to each assembly module in this way. Local, the labels, variables, constants declared local are to be used only by that particular module. Offset, it is used to define the offset or displacement of the named data item. ORG, it is used to set to the location counter is set to 0 when the assembler starts reading a segment. So, using the ORG we can give our own location, desired location for starting the code. It's proc, it's used to identify the start of the procedure. PTR, it's used to assign a specific type to the variable or the label. Segment, it's used to indicate the start of the logical segment like this. So, examples have been quoted here. It's short, it's used to tell the assembler that only one byte displacement is needed to code a jump instruction. Type, it's used to tell the assembler to determine the type of a specified variable. Plus and minus operators, these operators represent the arithmetic addition and subtraction. Far pointer, the label following the far pointer is not available within the same segment. Near pointer, the label following the near pointer is available within the same segment. Segment, it is used to decide the segment address of the label, variables or procedures. So, in this way we can have a lot many assembler directives for 8086. So, I have already discussed the most of them here in this lecture. That is all for the day. Thank you.